Hello everybody. So this video we're going to cover that page in the Unit 4 skeleton notes that we skipped in class. So that is page 3, and it starts with these 3 graphs and talking about thermodynamic considerations of a reaction. So thermodynamic considerations, we're thinking about the overall favorability of a reaction that's run in reversible conditions. Later, we'll talk about kinetic considerations, and in kinetic considerations, we're thinking about an irreversible reaction. But for a reaction run in reversible conditions, which remember that means if you have any starting material and it's forming the product, they're in some sort of equilibrium with each other, where the product, once it's formed, can also go back and form reactants. And so the overall favorability of a reversible reaction is the more stable molecule. So if the products are more stable, we mean lower energy, which also means less reactive. We use these terms a lot in class, so it's helpful to keep in mind if a molecule or atom or ion is more stable, that means it exists at a lower energy and is less reactive. And less reactive, lower energy, more stable than in this case, the other molecule in the reaction or whatever we're comparing it to. So we'll be comparing different molecules or atoms. So for thermodynamic considerations, we consider the delta G of the reaction, which really tells us if the reaction is exothermic or endothermic. So once a reversible reaction reaches equilibrium, the more stable molecules or the lower energy molecules or the less reactive molecules will be in highest concentration. So we can have 3 scenarios. The first will be an exothermic reaction, but for all reaction coordinate diagrams, the y-axis is G for Gibbs free energy or E for energy. Usually kilojoules per mole are the units. The x-axis is reaction progress. And so we can have an exothermic reaction. So thinking back to Gen Chem, this is a reaction where the starting material is higher energy than the products. So it still goes through some high energy transition state, but overall, products are lower energy than reactants. So delta G, which is the energy of the products minus energy of the starting material, is less than 0. Energy is released overall. And for this type of reaction, the lower energy, more stable molecule will be at highest concentration. We're going to label that with a pink star here. Lower energy is the products. So the product side will be in higher concentration. For an endothermic reaction, the products are higher energy than the starting material. Again, still goes through the high energy transition state, but overall energy is required for the products to form, so the delta G is greater than 0. And so at equilibrium, the more energetically stable molecules are at highest concentration. More energetically stable means lower energy, means less reactive, and for endothermic, that is the starting material. Then the last possibility, which is quite rare, but still possible, is when the starting material and the product are at equal energy. So in this case, the delta G of the reaction is equal to 0. Neither side is favored, so it's not endothermic, not exothermic. And by side, I mean the reactant side, so the reactants or the products. So at equilibrium, starting material and product would be in equal concentration. So again, these show the overall favorability of a reaction so long as the reaction is run in reversible conditions, meaning that the starting material can form products, the product can also form starting material. And so after time, once a reaction reaches equilibrium, more stable molecule will be in higher concentration. So now let's think if we cannot reverse a reaction. If when the starting material forms product, that's the end. Well, here now we're thinking about kinetic considerations. Kinetic considerations are related to how fast a reaction proceeds. So thinking about reaction rate, and here we're focused on activation energy. So let's say we have a reaction that can form two possible products. So we still have G and reaction progress. Starting material and two products can form, let's say, product 1 and product 2. Now let's also say that starting material to product 1 has about that high energy of a transition state. And then I'll use green here, and we'll say product 1 to product 2 has about that high energy transition state. And these are conditions that I'm setting. I'm giving you an example where we have two products, and I'm telling you this is relative energy of the transition states to form each of the two products. So transition state for product 1 is about there. Transition state for product 2 is about that high of energy. Under thermodynamic considerations, we'd say product 2 is in highest concentration because it's lowest energy. And that's only the case for reversible reactions, but we're saying we have an irreversible reaction, irreversible conditions. So now we're thinking about which product is made faster. The product made faster is the product with lower required activation energy. So for this example, the green path has higher activation energy, so it is the slower path. It is the slower reaction. So P2, even though the final product is more stable than P1, P1 is actually formed more so than P2 because it has a lower activation energy. It is a faster reaction. So starting material to form P1 is faster. So more of the P1, that product is produced because of the faster reaction. Now it could also be the case that we have starting material. Let's keep, let's say P1 is about this much energy and then P2 is higher energy. And transition state to P1 is lower energy than transition state to P2. Well, now I think it's pretty clear. P1, it is more stable, but also it has a lower activation energy, just like the first example. So the green pathway again is slower. So more P1 is produced because it has a lower activation energy. So lower activation energy, remember distance between, I guess I'll use black here to here is activation energy for reaction 1. And then transition state to energy of the starting material is activation energy for reaction 2. So higher activation energy means lower rate, slower rate. That's because activation energy tells us, and the energy of the transition state tells us how much energy the starting materials need to have in order to overcome that barrier to produce the product. So if more energy is required of the starting material, that takes more time for the starting material to absorb that energy. So higher activation energy, slower rate. Now, so far, all of these reactions that we've drawn today in this page are one-step reactions with one transition state. But I've mentioned in class that if a reaction has more than one step, then it has more than one transition state. And so if a reaction has more than one step, the rate determining step, the step that determines the overall rate for that reaction, is the step that goes through the highest energy transition state. We use that symbol for transition state. So let's do an example of a two-step reaction and let's say you were given, this is the energy of the starting material, here's the energy of the product, and then a two-step reaction. After the first step, an intermediate is formed. So the first step is starting material to intermediate, second step is intermediate to product. So let's say starting material to intermediate requires about that much energy, so we have transition state for step 1 there, and then intermediate to product requires about that much energy, and there we have transition state for step 2. For a two-step reaction, the rate of that overall reaction depends on the slower step, and the slower step we describe as the rate determining step, and that is the step with the highest transition state energy, and that is step 2. So this is the rate determining step. Which is often abbreviated as RDS, rate determining step. And we know that because it has the highest energy transition state. So with all of that in mind, and I briefly introduced that I for intermediate, let's go to the page, I think this is page 6 now, where we introduced on Thursday SN1 reactions. So let me just check real quick. Yeah, page 6. So page 6, we went through in class, we have SN1 reactions, looking at the mechanism. So see where I drew the arrow? We're looking at the mechanism. First step, we form the carbocation, and I wrote here that it is the rate determining step. We form this high energy intermediate and then the nucleophile bonds. Well, let's draw the reaction coordinate diagram before the video's over for this general SN1 reaction. So we will say, we're just going to say that the starting material and product are equal energy here. You would be told if it's overall exothermic or endothermic. But for this example, let's just keep them equal energy because we don't have real molecules in this example. Okay, so filling in the reaction coordinate diagram, we know that the first step is the rate determining step. So that means on the reaction coordinate diagram, that step must have the highest energy transition state, higher activation energy. So if I say that is the transition state energy for the first step, that forms an intermediate. Intermediates are still always lower than the transition state in energy. But in this case, the carbocation is certainly higher energy than the starting material and product because it has a carbocation. It has an open shell carbon. It has a charge. That's a high energy molecule. So I know it's higher energy than the starting material and product. And so we're just talking about relative energy here, and I just wrote in that that's the carbocation, the C+. So once the intermediate is formed, then we have another step with its own activation energy and own transition state energy, but we know that that is going to be lower energy because it is not the rate determining step. So right here, we have the rate determining step. It has a higher activation energy and higher energy transition state. So for all SN1 reactions, showing the two steps, because it's a two-step mechanism, the rate determining step is the first step where the intermediate is formed, and that will be the highest energy, highest activation energy and higher energy transition state. All right, I will end the video here. I'll see you all in class on Tuesday.